Good morning once again. We now come to the proper part, the actual part of the course. And I think maybe I'll just say a little bit more about the way we hope to organize this course, because this is the first time I'm doing it. Usually this is a one semester course, and we in the NUS system we have 3 hours per week. 3 hours lecture per week, and it's over 13 weeks. And so students would have time to go back and discuss and internalize the thing, and if they have questions, they would ask me or ask their friends, discuss with their friends. And usually a significant number of assignments, typically about five to six assignments. So it's about one assignment every 2 weeks, okay, followed by a final exam. I think this is a little bit more unique because we have to sort of do everything in 2 weeks. So I appreciate that there may be some difficulty because you may not have that much time to try to internalize that or to clarify the concept. So it is important that you if you have any questions, please ask me right away. Okay. The other thing is that if you look at your course notes, I think you all have your course notes, right? I think printed out. Yeah, it looks like quite a thick pile of paper there, and there is a fair amount of mathematics. Don't worry, I will try to where there's a lot of mathematics, I'll try to sort of like gloss over some of the mathematics and give you the conclusion, rather than to take you through the algebra, which is I think is not necessary, because I think you can go back and read through the algebra, and if you have questions, we can always discuss it at a later point of time. So that can be done. The main thing is to bring out the important points. So in every lecture, I will bring out some important points in terms of constitutive modeling. So I hope that this is and also the other thing is that I think Prof Juneja has has set up some Plexis workstation so that you can do some hands-on, especially towards the end, the last couple of days. I have also, in fact, I have also brought my own software. It's called GeoFEA, which I developed jointly with some of my former students. It's a software that's being alpha tested. So in a sense, you can download it free of charge. Okay. So and it's we like to think that it is a reasonably full-featured kind of software. So I know I'll show it to you, but the purpose is not to show you how to press button or to advertise the software, but I have run several problems on the software, and through those problems, I hope to use them as vehicles to show them how different models will actually behave. And I won't be too ambitious. I won't cover everything, because a lot of students ask me, can you just teach me the best model? Actually, the short answer to it is that there is no such thing as the best constitutive model. All right. I was talking to Professor Pandey many years ago, I think about 30 years ago. When I was a student in Cambridge, Professor GIAN Pandey from Swansea visited Cambridge, and we were talking about cyclic loading. And I said that there is this model which I read somewhere that seems to model the cyclic loading very well over quite a number of cycles. And he turned around to me, he said, how many parameters this model need? 300 parameters? You see, the problem is this, that you can always fit a curve very well if you have enough degree of freedoms, enough parameters. But when you come to, the emphasis on this is practical geotechnical analysis. If you are doing research in your PhD, you can always have a model that has something like 10 to 12 parameters. And I have personally also written, developed models. In fact, one of them, we just published it in the International Journal of Geomechanics on cement-treated soil, and that requires something like 10 parameters. But I don't expect the practical engineers to use this practicing. I don't expect you, if you go out to practice, to use this model, because first and foremost, the work that is required to extract the parameters for this model will be tremendous. And I don't believe that a practical engineer would have the time nor the expertise to extract all the parameters. I can tell you that 99.9% of the time, most geotechnical engineering analysis in practice is done using the famous more Coulomb. You know, I mean, this is the reality of life. And I think when you go out to work, you will be doing more Coulomb most of the time. You know, there will be some special small amount of time where you'll be dealing with the chem clay, and I'll be talking about the chem clay. But most of the time, it will be the more Coulomb, because the more Coulomb is easy to use. 4 parameters, that's all it takes. So that's the reason why there is a difference between constitutive modeling in research and constitutive modeling in geotechnical engineering practice. And I'm concentrating on the second one. Because in research, you can come up with the most fancy model. We can have tons of parameter. But when you go to practice, you have no such freedom. You can't do that. You just have to... I mean, if you have 10 layers of soil and each one requires 20 parameters, 200 parameters, how are you going to get that 200 parameters out? So that is always the issue. On top of that, some of these models, including possibly my models, very advanced models, have singularities. That means points at which they go unstable, which even developers like me may not be aware of, because I've not taken them through the full slate of tests. So as a result, you may be using something and then suddenly it just crashes, because one of the element in your finite elements basically hit a dead end in that model. And so that can always happen. You know, I was in Europe. I won't mention the name of the model because it's not so nice to. I mean, they in a conference and everyone is using. It's Germany, you know. Everyone was using a model. If you've been to Germany, you know what model it is. You know, everyone was using that model because one of the big men there is pushing his model all the way. And so I pull one guy aside, a guy that I know very well, my old friend, and I said, Ditat, this model is really something that can work. He said, Fook, don't believe half of it, because half the time or more than half the time when you run that model, it will just go about halfway, it will just jump out of the program because it hit a singularity. So that's the thing. It all looks very nice on paper, and when people present a paper in a journal or conference, it will all look very nice. Of course, they won't tell you how many times it jump out. You know. So, but there will be many times this kind of thing do happens with very complex models. That's why when you want to propose a model to a well-controlled software like Abacus, they don't accept any model. You can use the model yourself, but if you say, please quote this model as a standard model, they will not just accept it because they have to be sure that it just doesn't jump out as it feels like jumping out. That's one of the problem with modeling. So basically, what I would like to do to start with is to give you some background. I have been dealing with this course since the predecessor course to this, many generations of predecessor course to this since the 1990s, which is about 25 years ago. And in those days, we call it mechanical behavior of soil. And that was even before Professor Jineja came to NUS. And it was an 18 hours course. I was just talking about chem clay, whatever I learned from Cambridge University. But then in the early 2000s, we decided that because based on the demand of the student, they said that this course is very useful. Can you increase it to a 36-hour, 39-hour course? So we actually increased it to a 39-hour course. And so basically, that sets the scene for that particular that particular full course. But at the same time, there's a lot of this background event going on. And so I would like to tell you a little bit about this background event. Okay, the question is why geotechnical engineering and constitutive modeling? And I'll give you the perspective that I have, which is from a Singapore perspective, the kind of lessons that we learn and what, in a sense, shaped the landscape and haunted the mindset of geotechnical engineers in Singapore. And the big event that happened in Singapore took place on the 20th of April 2004. The date is very easy to remember, 2004. All right. So maybe it's I don't know whether you believe in numerology or something like that. They said somehow it is a bad combination of number 2004, 2004. I don't know. But anyway, something happened and there was a very deep excavation, 35-meter deep excavation in 30 meters of 30 to 35, almost fully in soft marine clay. When we talk about marine clay in Singapore, we're talking about soft clay, very high plasticity. just to give you some idea of the kind of properties, engineering properties of this clay, the undrained shear strength will range anything from 15 kilopascal to 25 kilopascal. That's the kind of undrained. So it's pretty gooey stuff. Right? The permeability is very low, 10 to the minus 9, 10 to the minus meter per second. The plasticity index is typically 50 to 55. So it's just a high plasticity inorganic clay. So it's a bluish material, you know. You probably have such material around the coastline somewhere, you know, especially down south. It's quite common in the Southeast Asian region. So we call it Singapore marine clay. And that this excavation took place in 35 meters of Singapore marine clay. And there was, on the 20th of April 2004, there was a major collapse, and you can see this major collapse. And this excavation took place because it was required to cast a tunnel box at somewhere around, the base level is around 35 meters below the ground surface, 35 meters. And when it get down to about 32 meters, the thing collapsed, you know. And so, because of this collapse, the number of people who lost their life is not many. There are only 4 persons lost their life. Actually, it should not. It's terrible to say only 4. Even 1 is too many. Even 1 is too many. But the main thing is that the loss to the companies, the loss to the company. The Japanese contractor was the one, the main contractor, Nishimatsu, was the one in charge of this site. And my Japanese friend told me that Nishimatsu lost about $300 million on this particular project. And they had to sell their properties in Japan to pay off the debt. So that is how bad it is. So basically, it's a major incident. And so that led to a whole series of events. And you can see points there. It says lessons from the Nickel Highway collapse, the PE Geo and ACE. I'll talk a bit more about this later on in the MSc Geotech. Okay, maybe before we even get to the 2004 event, maybe I'll bring you back to the start. As I can see, the very first day, the very first moment when FEM was used in Singapore. Now, FEM means finite element modeling, or finite element analysis, FEA. Now, you probably would have known, and Professor Juneja did mention to you just now, in a lot of traditional geotechnical design, especially those things that you learn in the undergraduate, it's all based on total stress, limit equilibrium. You never need to know anything about the stiffness of the material, like the modulus, constitutive model. You don't even need to know the K0, the lateral. All you need to know is C dash, V dash, or C phi. Something like CU, phi U, that kind of thing. So basically, all you need is the strength parameter, because you're really designing against stability and you just want to have a factor of safety. Now, that was the case back in the 1970s in Singapore, where there was a lot of foundation engineering work. Now, the situation starts to change in the mid-1980s. And the mid-1980s, the situation changed because we developed the first mass rapid transit, part of which was underground. At the same time, buildings were running out of space because there was new requirement that says that if you want a building this tall, you must provide car park for so many cars. That's the new planning regulation. And so building owners found the need to have to provide car parks for their building. And so the most convenient way is to go down below ground surface. And so that led to a lot of deep excavation. And excavations in Singapore, deep excavations in Singapore, the deepest that I have ever participated in was about 30 meters. It's 6 level down excavation. So B1 to B6, you know. So basically, that was a time when all this started. Now, when this thing started, the Mass Rapid Transit Corporation has also got guidelines relating to, if you dig a big hole in the vicinity or in the proximity or neighboring an MRT, for those of you who are going to work in Singapore, this may be important because I know that there are many Indian graduates working in Singapore. This is going to be important. If you build something next to a station or station box or tunnel, whatever it is, the rule is very strict. No part of the MRT structure must move by more than 15 millimeters. All right, which is about that much, 15 millimeters. That's the kind of allowable movement. So then the engineer has to justify to the authorities that by digging a hole, it will not cause it to move by more than 15 millimeters. Okay. Now that poses a big problem because traditional limit equilibrium analysis doesn't give you any numbers on ground movement. There's no ground movement at all. It's just factor of safety. And the question always is, how do you translate factor of safety to ground movement? You can't. So basically, that is one of the problems. The second thing is that, okay, in the early days, in the very, very early stages, people were using charts like Terzaghi and Peck and things like that. But it was found very quickly that those charts are not sharp enough to provide the kind of numbers you need, which is about that much movement. So basically, they start looking for other things. And so ground movement doesn't just mean lateral movement, but it also means surface settlement, ground settlement. There's also rules governing how much the thing is allowed to settle. Okay. So anyway, the backdrop of this is that the first use, as I know, of finite element analysis in Singapore was back in 1989. At the Central Expressway, the tunnel is called Chin Sui Tunnel. There was a tunnel that underpasses the Singapore River, and it was decided to use FEM because in the middle of the excavation, the wall actually, the diaphragm wall actually moves out by something like 200 to 300 millimeters. All right, and the road was declared a danger zone because it was in danger of collapse. Okay, all the curbs went buckled up, so it was quite a scary sight. And so we were called in, and that was when I happened to be co-supervising a PhD student who was writing his own software. At that time, and in those days, there was no Plexis. All right, there was not even Sage Crisp. Okay, so there was nothing. So we just used our own program and we just analyzed the thing. And that was the first, I think, to my knowledge, our first experience using FEM for a construction project. Okay, and of course the model we used was none other than the Moore-Coulomb model, which is, I think, still being used, the most widely used model. Then in 1992, Junction 8 Bishan was my second experience. Again, that was a big building with a big basement, and so we had to use it. And it was not very well used in those days in practice. And in those days, what happened is that whenever the consultant needs to use FEM, they come to the university. They'll come to the university and say, can you please run some FEM for us? Finite element analysis for us. Then around 1995, 1996, there was this program that came up. Many of you will probably not be aware of this. It's called Sage Crisp, a very early version. When you look at the graphics on the screen, it's totally crummy. It's not very high-level graphics. It was like, I'm not sure whether it was before. Maybe it's just around the early Windows version. Not very user-friendly. Then around 2000 onwards, Plexis came in. And Plexis was very user-friendly. It was a big step forward in terms of user interface. And suddenly, engineers outside now found, in Singapore, everyone found that, hey, I can actually press a few buttons and get an analysis done. And that was a good thing. It was also a big danger because the buttons are so easy to press. But do they know what the buttons mean? See, that is the big question. And the nice thing and the bad thing about Plexis, the nice and the bad, is that it makes a lot of assumption for you. And it doesn't necessarily tell you what assumption it is making. And so I feel that it is part of the purpose of this course is to tell you, when you look at this parameter and it has this value, this means this is what it does to your analysis. So that you use it like an intelligent user, a knowledgeable user, not just pressing button. Okay? And it was so friendly that it's so easy to construct a mesh and run that, in fact, it is no longer for practicing engineer then to come to NUS or NTU, Nanyang Technological University, to come and say, Prof, can you run it? They don't need to do that. They can do it in their own office. It's easy. The PC can do it for them. They just run it on their desktop. But there's a big danger because a lot of them were not really, there was a case where, just to give you an example, one of my friends was visiting a contractor's office, and there was this young engineer just fresh out of NUS, maybe NTU, punching away on plexis on a computer, in front of a computer. And my friend just asked a simple question. Can you tell me where is the finite element? Or what is the finite element? And you know what the guy turned around and said, actually, I don't know. No? You see, what he doesn't realize is the finite element is the grid. All the things in the big grid of things that he's looking at are the finite elements. And the finite elements is so called because they are elements of finite dimension, not infinitesimal dimension, not infinite dimension, but of finite dimension. And that's why it's called finite element. And you can just imagine this guy has your life in his hand. I mean, would you dare put your life in his hand? That's the big question. And so when I heard about that, I mentioned to someone that at the rate the things are happening in Singapore, there is an accident just waiting to happen. Just waiting. It's a time bomb. Because people who has access to this powerful technology has no understanding on how. It's like you've got your finger on a nuclear button, but you don't know what the nuclear bomb is going to do. Wow, that's the dangerous thing. So, and the worst thing is that some of my fellow academicians were going around telling people that plexis is so powerful, you don't need to know soil mechanics. And I said, nothing is further from the truth. That is complete BS. The more powerful the software is, the more soil mechanics you need to know, because you want to be in control. You don't want to let the software take over control. That is the most important thing. So when people ask me, hey, what is the best model? I said, there's no such thing as a best model. There's such thing as a best modeler. That means you go in there, you are in control. You can do very nice things with a very simple model if you know where your limits are and how to adjust your parameter to get sensible answers. There's no such thing as an all singing, all dancing model that will just one press. I don't care. If that day happen, I think it will be a sad day, to be honest, for geotechnical engineer. Because what it means is that a guy fresh out of primary school can just, and out comes a beautiful analysis. Who the hell will ever need any more geotechnical engineer? Geotechnical engineer will cease to be relevant. A high school student can do that. A middle school graduate can do that. So you don't need a geotechnical engineer. So that will be a sad day. So anyway, I told people that there is an accident waiting to happen. And true enough, in 2004, Nickel Highway happened. So that was the thing. And after the Nickel Highway, there was a big committee of inquiry. Now I've got the entire report of that committee of inquiry. So if you want, I can actually download it somewhere. If you want to read, you can read. It's a very thick report, But it's contains some very nice information on the project, why it failed and why, how the project is managed and what led to the failure. But here I captured the gist of the finding. And the gist of the finding was that the collapse was rooted in two critical design errors in a temporary retaining wall system. The first is related to geotechnical issue. The second is structural issue. It's actually connection, strut to veiler connection. So I won't bother with the second one, but the first one is something that you need to pay attention to. And it says here, the use of method A in the C824, this is the contract, C824, contract 824 project, to model the undrained behavior of soft marine clay was wrong. The method over-predicted the undrained shear strength, underestimated the wall bending moment and deflection, and resulted in the under-design of the retaining wall. Method B, now this, don't worry about what is method A, because I'm going to tell you in detail. Sometime tomorrow it will happen. Okay? So method B should have been used in this circumstance, and the use of method B instead of method A instead of method B resulted in an underestimation of the predicted bending moment and deflection by about 50%, or a factor of 2 for the original design of the M3 wall, which is the wall that collapsed. So basically, what it says is this, that because a wrong design has taken place, all right, the wall was under-designed by a factor of 2, and that basically contributed very significantly to the failure. To me, that is a valuable lesson. And because of that, there was a whole string of events taking place. And so maybe I'll just say something about this event, coming back to this. Okay. Now, following the Nickel Highway collapse, the government suddenly realized, for years, I mean, geotechnical engineering is not new. Geotechnical engineer also not new. We have been like animals running around, for like decades, and yet nobody took note of us, right? Because they don't see the foundation, they don't see the power. The power is on. They only see the structural engineer. And suddenly, in the committee of inquiry, everybody was talking about, all the expert witnesses start talking about constitutive models, angle of dilation, and all kind of things relating to finite element analysis. And you can imagine the lawyer leading evidence for the state, okay, was himself a civil engineer. But he's a fresh graduate, civil engineering, fresh graduate. And I can tell you, he was totally lost. Can you imagine a fresh graduate going out there and listening to all these things about flow rule and all the thing about U surface, U criterion, and I tell you, he doesn't have a clue where things are coming from. So imagine the main lawyer leading evidence for the government was lost. It was then they realized, hey, there is this animal running around called geotechnical engineer, which somehow has not been visible to us, but he has been doing all kinds of terrible things. So we better start to regulate them, And so that was when the regulation starts, okay? And so in the old days, there was only one type of professional engineer, and that's called civil. If you are civil, if you're electrical, then electrical, but civil is only civil. So the requirement for civil engineering PE is not very high. You get a graduate, you go out, you get a first degree, you go out there, practice 3 to 5 years, you are licensed as a professional. And thereafter, for the next 30 years, you are just a PE civil. Now, because of that, the government said, no, this cannot continue. We need specialized people to use this class of new technology. And so as a result, they formulated a new class of professional engineer called PE Geotechnical, which is called Geotechnical Specialist Professional Engineer. Geotechnical Professional Specialist Geotechnical Engineer. And one of the basic requirements of a specialist, geotechnical specialist professional engineer is that you must have a postgraduate degree majoring in geotechnical engineering. This is the basic requirement. Of course, you need years of experience, and you have interviews. And I am actually on the interview board that conduct all this interview. And the failure rate actually can be quite high. In the early days, the failure rate was 75%. Okay, so it's actually quite a demanding. So basically, this is a new class of professional engineer. So to be a geotechnical engineer, you need to be a professional civil engineer first. Then it's like a doctor. You first have to be a GP, general practitioner. Then you become a specialist consultant, and so on and so forth. So now they are creating these particular systems, a tier for people to go up. And then on top of that, you got the accredited checker geotechnical engineering. So this is there are only I think 2, 3, or 4 geotechnical accredited checkers in the whole of Singapore. So you can imagine the moment you get your PE Geo, and there are something like 50 to 60 professional geotechnical specialists in Singapore signing things for all of Singapore's projects. So you can imagine, this is very, very coveted. The PE Geo and the AC Geo over there are very coveted. The PE Civil are not so coveted because there are 4,000 civil engineering professional engineers. By contrast, there are 60 geotechnical specialists. So the moment you get a geotechnical specialist, you can literally walk up to your boss and say, you got to pay me extra, otherwise I'm leaving. Because there will be people outside looking for me. Okay, from what I can gather, typical salary range, typical minimum starting salary for a geotechnical specialist professional engineer is about $12,000 to $15,000 a month, Sing dollars a month. So this is a big jump from about $5,000 to $6,000 that before. So that's why it's very covered. And people actually have written to minister to protest and say why didn't they get through the interview and all. So this is a part of the story, but this is the thing. So they basically, because of that, they have this thing called professional geotechnical, and because of that, NUS started to mount a course called MSc Geotechnical Engineering. Basically to prepare people for this geotechnical engineering, professional engineering interview and exams. So this is essentially what it's all about. And this course is one of the fundamental courses they have to take. It's called part of the analytical package. The analytical package. So this hopefully gives you the kind of background to what this course is all about. Now we come a bit to the sort of moving a bit to the technical side of the thing. Basically, now I think that I just want to capture a little bit of the history of geotechnical engineering design. In the early days when we are doing undergraduate, I think it's still pretty much the same because I teach the same thing to my students in the undergraduate. When you want to design a slope or you want to design a retaining wall, what do? It is limit equilibrium. You do the earth pressure or you do the Coulomb wedge or you do this kind of, there's a standard thing that you would do. So basically, these are the kind of thing. And usually at the end of the day, what you want to get is stabilizing forces over overturning forces or stabilizing forces over destabilizing forces. The number is captured in something called a factor of safety that you need to have a certain minimum value to pass. And that minimum value can be subjected to a lot of argument. I've seen people going up to the pre-litigation stage, and they were arguing over factor of safety of whether factor of safety of piles should be 2.5 or 2.25 or 2.0. I mean, honestly, I look at them, they look at me, I said, your guess is as good as mine. I also don't know what to tell you. Because, I mean, on what basis am I going to tell you that you need 2.5 and 2.25 is not enough? For example, in retaining wall, you look at the caissons in Singapore, they do for land reclamation work. We typically use 1.5. The Japanese are very gung-ho. They use 1.25. Now, how am I going to tell the Japanese that 1.25 is not sufficient? The Japanese, I have more experience designing 1.25 than you designing 1.5. But, I mean, this is where the big problem lies, and there's no real physical connection between a number that you call factor of safety and the actual performance of that thing in the field. That is the big problem with the factor of safety. The other thing is, of course, people don't know what this factor of safety is supposed to factor. It can factor a whole variety of things. So anyway, this is one of the drawbacks. I won't dwell on this thing. The second one is called the limit state, which is more the Eurocode kind of thing. You know, the EC7 Eurocode. Do you use Eurocode in India? Okay, EC7 is one of the most, if you go overseas, in Europe especially, I won't say throughout the world, because the Americans still don't buy it. The Japanese still don't buy it. All right? But the Europeans are trying to sell it to the whole world. Okay? And Singapore bought it. I don't know why, but anyway, we bought it. Anyway, it basically means breaking up the factor of safety into a lot of little partial factors. But at the end of the day, you're still factoring. You're still factoring things. You factor strength, you factor this, you factor loads, you factor all kinds of things. It's a bit like structural design. So basically, it still has the drawback that you cannot predict what is the working load behavior, because all you can tell people is, I now meet the requirement of the code and it has the required factor of safety. But at the end of the day, LTA is the government, the Land Transport Authority in Singapore says, can you assure me it will not move by more than 15 millimeter? Now, how do you say that? I meet all your factor of safety in the EC7, therefore it will not move more than 15 millimeter. You can't. There's no argument you can make along that line. So that is still a problem. So that's the reason why that's why a lot of people are now looking at finite element as a way out. And I think that Plexis came in at the right moment where there was a big interest. Okay, do you do a lot of FEM in geotechnical design now over here? Okay, but when you go into, I think when you do things like deep excavation, or tunneling may not be so important, but deep excavation in a city area like center of Mumbai, I think you probably will need a little bit of FEM to help you to get some feel of the ground movement. That's the kind of thing. But of course, you are doing classical foundation design. I think factor of safety is as good as anything. So basically now, because in Singapore now, underground development is a major issue. Therefore, there is a big thing about using FEM. In almost every deep excavation or tunneling project, you cannot start work unless you have at least one proper finite element study. At least one proper finite element. Usually more. usually more, but at least one. So every consulting company will have a whole series of computer running plexis. All the big guys, ACOM, TY Lin, all this they will have, Savannah, Jeep CPG, all this they will have their own computers running all kind of things. So basically Golders, all this they will have computer running. Typically Plexis, it will be Plexis. So basically that is why it's a very prevalent thing. You cannot roll it back in Singapore, it's impossible. There are too many people using it. Okay, so basically because of that, we need to, this is the background, this gives us this sort of like, forms the background to our course. And that's the reason why I think we need to know a little bit more about what constitutive modeling is all about and what different constitutive models does in detail before we use the FEM. That is the motivation to this particular thing. Now, the first part of this, I'm going to move through a little bit quickly. The first part is probably revision for some of you, because I know that the audience here is quite diverse. And I am not aware of most of your background, I'm not aware. But I suspect that I have to sort of like take a minimalist approach in the sense that I have to assume kind of a lower baseline so that we don't miss some of you. But if you have questions, please ask me. Okay. So the starting point of that is to first revise a little bit on our basic fundamental concepts of stresses, and strains. The first thing is that most finite element analysis assumes the ground as to be a continuous medium. If your ground is not a continuous medium, then you have to make allowance by introducing some discontinuity somewhere. Okay, but usually that is the basic assumption. Now, I won't go through the concept of deriving stresses for you because I think that is something you probably can do that by just reading the notes yourself. But essentially, the main thing is this, that if you want to do a three-dimensional analysis, you need 6 stress components to completely characterize the stress state on a three-dimensional point in three-dimensional space. Firstly, you need three normal stresses in the x, y, and z direction. I assume that you have somehow fixed the x, y, z direction. So you need the three normal stresses in the x, y, and z direction. And then you need 3 shear stresses. 3 shear stress. Tau xy, tau yz, tau zx. Okay, 3 shear stress on the same point. So you have 3 sets of normal stresses and 3 sets of shear stress. So in totality, you would have 6 independent stress components. So the first important point, I won't go through to tell you that complementary stresses. This one, my impression is that my guess is that you probably would have covered that in your undergraduate. But if not, you can just take moment of an element around the center. You can actually easily show it to yourself that it will be okay. So essentially, there are 6 independent stress components: sigma x, sigma y, sigma z. Some people are a bit more rigorous. They'll say sigma x, sigma y, sigma z. I'm a bit lazy. I just say sigma x, sigma y, sigma z. But it's the same thing. All right, 3 normal stresses and 3 shear stresses to characterize the full three-dimensional state of stress in three-dimensional space. Now, in corresponding to the 6 components of stresses, okay, 6 components of stresses, you also can define 6 components of strains. 6 components of strains, okay? 3 normal strain components, which is epsilon x, epsilon y, epsilon z, okay? And then gamma xy, gamma yz, gamma zx. These are the shear strain components. So 3 normal strain, 3 shear strain that completely define the state of strain on a three-dimensional space at any point. Okay? Now, just a little bit of detail on the strain. The normal strains are defined, of course, in terms of extension. You got an element starting here. It has extended by a certain amount or compressed by a certain amount. The ratio of the compression divided by the original length is the normal strain. Okay, so that is fine. Now, the shear strain is defined in a funny way based on angle, but I won't go into it. It is actually given in the notes. This slide actually explain the definition of the normal strains. Okay, so I don't think we need to go through that in detail. We'll just skip that. Now, the shear strain is defined in terms of angular distortion. The first thing is that I want to say a little bit about the shear strain here, because the way you normally look at shear strain, in definition of shear strain, is let's start with a block of material like that, which is a rectangular form. All right, assume that there is a rectangular block of material at this particular point, and then you look at how that rectangle distort, that imaginary rectangle distort after you have strained it. So basically, after distortion, it may take on the form of a diamond shape. All right, a diamond shape. And so when you look at this angle was originally 90 degrees, and now this angle is no longer 90, it's 90 plus alpha, which is this small thing over here, plus beta, which is this small thing over here. So the additional angle is alpha plus beta, and that is the definition of the shear strain. This is how the shear strain is defined in terms of angular distortion. This is the classic definition of shear strain. So basically, without going too deeply into the mathematics of elasticity and stresses and strains, I hope to sort of just bring everybody up to speed on stresses and strains. Now, I'm not going to say much more about stresses and strain definitions over here, but is there any questions that you would like to ask at this point of time? Clear? Okay. If not, then let's carry on. Okay, so the next thing, this part of the course, which is the whole of today and plus a bit tomorrow, is on basic elasticity. But even through basic elasticity, I hope to be able to capture some important points when you do your FEM analysis. And even that, there's some. Now, you have the stresses on one hand, 6 stress components, and you have 6 strain components. All right. So obviously, you need to be able to relate all the stress components to the strain components. Okay. Now, the parameter that relates the stress component to the strain component is the parameter that we very widely call modulus. All right, I think you all heard of the modulus. And the Young's modulus is something I'm sure you would not be unfamiliar with. It will be something that you'll be very familiar with. But I want to use this section to highlight one point. That as a geotechnical engineer, you're not just dealing with the Young's modulus. You're actually dealing with a few different types of modulus. And I hope to bring some of this modulus to you so that you are conscious, and when you deal with people across in practice, and when they bring out the modulus of this is so much, you need to clarify with them, are you talking about the Young's modulus, or are you talking about the shear modulus, the constraint modulus, the bulk modulus, or some other modulus? Which modulus are you talking about? Because sometimes geotechnical engineers define their own very special modulus. So we have to be clear, and they don't mean the same thing. Okay, now what is the definition of a modulus? So what we have here is that a block of a soil element here subjected to a normal stress in the x direction. And of course, if you look at this, you compress this block in this direction, it is going to shorten in that direction. So basically, if you compress this block in this direction, while keeping the 4 phases, that is the top face, bottom face, the front face, the back face, unconstrained. All right, unconstrained. That means that when you press this, it's going to grow fatter this way. It's going to grow because that's a Poisson's ratio effect. That's a classic. All right, and so as a result, when you compress, it is free to sort of bulge out in the other 4 planes. That compression. All right, the modulus that you measure is the Young's modulus. Now, what it means is this. If you measure the strain based on the compression of this thing, and you take the ratio of the strain as a factor factored by the stress, sigma x, that ratio is the Young's modulus. So therefore, in this situation, only in this situation when the 4 phases are completely unconstrained, the modulus you measure will be the Young's modulus. If you constrain all the 4 phases, it is not the Young's modulus. It will give you something that's higher than the Young's modulus, and it's the constraint modulus. So that's why you even at this thing, I would like you to sort of walk away understanding that when people talk about modulus, I need to be a little bit more careful, just a little bit more careful and inquisitive to find out what modulus are they really referring to. And you'll be surprised. Even in Singapore. In fact, in Singapore, a lot of engineers, they talk modulus, and you ask them, what modulus, huh? They say, I don't know, you know. You see, that's the danger, because people keep talking about modulus like it's their second nature, and then when you ask them, what modulus? The guy looked at you as if, you mean there are different modulus? That's the kind of thing. So this is the situation. Hopefully, you see, you can define different modulus, and I'll show you how to define different modulus afterwards. Okay, so this gives you the definition. In fact, the first equation over there gives you the definition of the Young's modulus, but only subjected to these four phases being unconstrained. Okay, and because the four phases are unconstrained, they will also suffer movement. The x, let's say, I usually take the y to be the vertical. Okay, so epsilon y is going to grow this way. Okay, and epsilon z, which is the front to back, all right, strain, is going to move out this way because of the Poisson's ratio effect. And of course, they are all related to epsilon x by the Poisson ratio, or rather the negative of the Poisson's ratio. The negative of the Poisson's ratio. Now, there's an important thing in soil now. And in soil, one of the things that we usually do, in Plexis, they assume this. Similarly, in GeoFEA, they also assume this convention. Compression is positive in soil, quite often. This is not wrong to assume the opposite. It's okay. Abacus assume that tension is positive. They also do soil, but they are more general program. More general program. So they have to cater to the wider kind of user, range of user. But Plexis assumes compression is positive because most of the time soil is subjected to compression. So if you say tension is positive, then very often you have to tag on a negative sign to all your numbers, and it becomes rather inconvenient. So people just do it the more convenient way by saying, oh, I'll just take the negative to be compression. So similarly, compressive strain is negative. Compressive stress is also negative. Okay, so basically you can now write, basically subject to this three, just this simple stress alone, this simple stress situation, sigma x alone, you can write out three equations on the three normal strains, epsilon x, epsilon y, and epsilon z. Just to emphasize, y is the vertical direction, and the z is the direction coming out the board towards you, the front to back direction. So, okay, so these are the three directions. Okay, now if you have the same body subjected to now the same situation, but now the stress acting in the y direction, the other four phases are still unconstrained, you can write a similar set of equation, and we don't have to go through the whole set of logic again. You just change x for y. You just change x for y, and that's basically what it is. Change the x to the y to the z to the x. That's how you do it, cyclical, the whole thing. And similarly, if you have a stress now in the front to back direction alone, front to back direction, but no stresses in the other two directions, you can also write the same thing. So basically now you suddenly end up with 9 equations. The first equation expresses the effect of sigma x, the stress in the x direction. First set of equation 13 to 15, expresses the effect of the sigma x, the stress in the x direction. The second set of 3 equations expresses the effect of sigma y, the stress in the y direction. The third set of 3 equations expresses the effect of sigma z, which is stress in the z direction. So the big question is, what if we have a very general situation where we have sigma x, sigma y, sigma z? We use the classical civil engineering method called superposition. You just superimpose all 3. So the strains will all just add up. So the strain in the x direction from the sigma x will add up with the strain in the x direction. So for example, the strain from epsilon x from here will add up with epsilon x from here, and it will add up to epsilon x from here, which is the second here. That's very simple. Similarly with epsilon y, epsilon z. So everything will add up. So you now have a combined set of 3 equations which expresses a general stress situation for 3 normal stresses. So when you do that and you add up, you got this three equations, which is really the 3 general equations for the 3 normal strains. Okay, and you can see that the normal strain epsilon x is dependent on sigma x divided by the Young's modulus, but also the negative Poisson effect of sigma y and sigma z comes into the picture. So this is sensible. All right. Same thing with epsilon y and epsilon z. So these are the 3 equations relating normal strain to normal stress. Normal strain to normal stress. Now, the effect of a shear stress is to cause a shear strain, and that is very straightforward. It's always a one-to-one relationship. The shear strain is equals to the shear stress, gamma xy is equals to tau xy divided by the shear modulus. Similarly, gamma yz equals to tau yz divided by shear modulus, and so on and so forth. Where the shear modulus, in fact, can be related to the Young's modulus and the Poisson's ratio by this simple relationship. The shear modulus is equal to the Young's modulus divided by 2 times 1 plus the Poisson's ratio. Okay, so this is the way it works. And so essentially now, if you look at it now, we now actually have a set of 6 equations. This whole thing together, this whole thing taken together is a set of 6 equations that you can actually say this 6 equation expresses the relationship between strain and stress in a full 3-dimensional space in an elastic material. So in fact, it is a generalized Hooke's law, a generalized form of the Hooke's law. And so you can express the whole thing in a matrix. Now, the first thing you must understand is this: when you play with a finite element program, internally and unknown to you, of course it's invisible to you, the program is playing around with a 6x6 matrix whenever it has to set up a relationship between stress and strain. It's always playing with the 6x6 matrix. So the only question is, what is this 6x6 matrix that it is playing with? So there is always a 6x6 matrix. And this is for full 3-dimensional analysis. Now, this relationship over here, this equation over here, okay, expresses the strain in terms of the stress. Okay. Now you can also express the stress in terms of the strain by solving this equation, this set of 6 equations. At this point, I'm not going to solve this equation for you on the spot. I just urge you to trust me, and this is the solution. All right. So if you want to check it out, please go ahead and check it out. There's no problem, But I think to solve 6x6 in this session to me is a kind of waste of time, So just take it from me. That this is the form, the equation form relating stress to strain. And this is the stress strain. This is what we call the stress strain relation. Oops. This is a stress strain relation. This is a stress strain. And A is a parameter, is a constant given by E over 1 minus 2 nu into 1 plus nu, where nu is the Poisson's ratio. Now, the other thing is, I want to sort of you to note at this point of time, and that is that if you have a linear elastic material, isotropic linear elastic, it can be proven mathematically that you need only 2 parameters to completely characterize that material. Of course, the usual combination is Young's modulus and Poisson's ratio. That is the usual combination. But that is not the only combination. You can, in fact, in finite element, a more typical combination is to use the bulk modulus and the shear modulus. Okay, but whatever it is, they are all related. You know 2, you can know all the rest. So therefore, if you know the Young's modulus and the Poisson's ratio, for a linear elastic isotropic material, you can almost derive all the other modulus. You can derive anything. They are all related. Okay? So you can express the whole thing, that's stress-strain relationship, in terms of the bulk modulus and the shear modulus. Okay? The bulk modulus is given by E over 3 into 1 minus 2 times the Poisson's ratio. If you express the whole things in terms of bulk modulus and the shear modulus, you can show that this matrix here, it can be re-expressed in this particular form. This is the form. And this is the form that a lot of FEM programs actually prefer to use. Bulk modulus and shear modulus. Okay? Bulk modulus and shear modulus. So this is how, and this matrix over here, dE, D superscript E, which I just used D superscript E to represent, is actually the elastic stress strain matrix. Alright? If you have an inelastic material or elastoplastic material, then we usually use the term D superscript EP, elastoplastic. And it is still 6x6, except that the coefficients are different. That's all. Okay, so internally, this is how the FEM program actually sees the stress-strain relationship. So whatever number you put into your assignment, it will go towards calculating this thing. It will go towards calculating this thing. Okay, now I want to say a bit about two-dimensional problems. The first type is plane stress. I think I will skip the plane stress because the plane stress is not so commonly done in soil mechanics. It's more commonly done in structural mechanics for thin plates. Okay, now there is a slight difference between plane stress and plane strain. Okay, in soil mechanics, in geotechnical engineering, we tend to deal more with plane strain. In fact, in a lot of 2D analysis, the only option you have is axis symmetric or plane strain. Correct or not? If you look at programs like Plexus, it's always axis symmetric or plane strain. There's no other thing. So plane strain is a common thing. People do an excavation, they'll go plane strain. And it doesn't matter if the excavation is in reality 3D, but they never mind, they'll just go and do a plane strain anyway. And then when you ask them, why plane strain, I don't know. Everybody use that one. So I use that. I'm no different. I'm not more right and I'm not more wrong than the next guy. That's the answer they'll get. But really there's not a good reason. And I think that we need to understand plane strain a little bit better. So I will skip the plane stress part since it only applies to structure. And I'll say a little bit more about the plane strain part, which is something that as geotechnical engineer is more relevant to you. Okay? So let's flip the thing and we move over to the plane strain analysis. Now, what is a plane strain analysis? There is a very strict definition of a plane strain analysis. A plane strain analysis is one, when you take a 3D thing and you kind of chop it up and then you take a section view and say this is plane strain, the basic assumption is that in the out of plane direction, when you're looking at the computer screen, the thing coming out at you, that direction, the normal strain is zero. It's completely constrained. Every frame, every slice is completely constrained. That is called plane strain. There's no normal strain in the out of plane direction. So epsilon z, z meaning the out of plane direction, is zero. No strain. So epsilon z is zero, gamma yz is zero, gamma zx is zero. Okay? And you can show that under these conditions, if you now revert back to the 6x6 equation, and you plug these numbers into it, all right, you can easily show that the 6x6 equation reduces to a 3x3 equation. So when you have plane strain, the work of the computer is reduced tremendously because instead of 6x6, now the guy is dealing 3x3. You know, so basically that is the attraction. So computationally, it is a lot less workload. Okay. The only thing is that a lot of people say, plane strain conditions are very commonly encountered in problem that involves a great length in the out of plane direction, like a tunnel, a line of tunnel, or a deep trench, a long trench in this direction. Now, actually, we need to think a little bit more carefully, and I'm not saying that we don't use plane strain. I think we will still continue to use plane strain, but we need to use it with a bit of care and with some knowledge of the limitation of the plane strain assumption. And that is that, and one of the problems I want to say is the plane strain this big thing about plane strain, which I feel is very, very widespread, very prevalent in Singapore, and I think very prevalent over the world, is because, when the professors write a book in geomechanics, when you talk about a retaining wall, when you see a classical textbook, what do you see? A slice. So the student go back and he think this is two-dimensional. The world is two-dimensional, but he doesn't realize the world is three-dimensional. But the professor screw up the whole thing and represent it as a two-dimensional thing. You know what I mean? So basically, people like me are partly at fault to be blamed for this two-dimensional thinking. So basically, supposing you have a tunnel, a lot of people say, I analyze a tunnel as a plane strain. That is a basic assumption, You know what is the basic assumption? Firstly, the soil condition is completely uniform throughout the whole length of the tunnel, which obviously it is not entirely. Maybe it is fairly uniform, it's still okay. But the other big assumption is, when you dig a tunnel, suddenly this whole thing went empty at one go, from plus infinity that direction to minus infinity. It cannot happen. You got a tunnel boring machine. You got a heading. Similarly, when you dig a trench, I can't see a machine so fast that can just lift up the whole piece of ground and then left you with a trench. You cannot. So basically, the guy is digging, and at the tunnel heading, there's always a three-dimensional stress state occurring. So there's something that we need to be a bit more mindful about. That even in problem that looks like it is plane strain, very often it's not fully plane strain. But if you use it in a knowledgeable way, it's okay. You know. Okay, now I have sort of, in a very quick way, covered elasticity in a total stress context. But the thing that makes soil different, and I think soil is so interesting, geomechanics is so interesting, is because there is water in the soil. Right? And water is the thing that makes our life so interesting. Water in the soil. Okay? And because you know why? When there's water in the soil, the structural engineer cannot handle it. Alright? I have a good friend who is very well known in Singapore for his pre-stressed concrete work. Very well known. He's a very well known guy. He's a protege of Professor T.Y. Lin. You know Professor T.Y. Lin of UC Berkeley? The great man and he went for, he was trying to get his PE geotechnical specialist PE. But he was no geotechnical specialist. So in preparation for his PE, he came to me and he said, Fook Hao, I understand they're going to ask a lot of questions about drain, undrained, and consolidation. Can you tell me a little bit more about, and this is a senior guy, 55 years old, 57 years old, asking me, what is the concept of drain and undrained and consolidation in geotechnical engineering? So I said, okay, no problem. You probably have studied it in your undergraduate, but I will just go through some basic concept with you over, and I spent 1.5 hours with him, sitting down and just going through the whole thing. After 1.5 hours, he stood up. He said, actually, I still don't understand what the hell is going on. Why you all have to make life so complicated? and then I realized that actually the concept of effective stress, soil-water interaction is not as simple to accept as most of us would like to believe. Or many of us would like to think of it as a second nature. But in fact, if you ask a structural engineer, it's actually something totally alien, to what they have been dealing with, because they never dealt with this two-phase thing before. So as a result, I thought maybe I want to spend some time. And there are some nice implications coming out of thinking about effective stress, especially for the undrained problems. And the thing is, we all know that if you have saturated soil consists of two phases. You have pore water and soil skeleton. And it really is the interaction of these two phases that gives soil all the interesting features a lot of interesting features that we see. And the effective stress is a concept started by Carl Terzaghi. I think you know Carl Terzaghi, right? To characterize the contact forces between soil grains in the soil skeleton. And when I talk about soil skeleton, it is the assemblage of all the soil grains. Okay? Now, usually, the higher the effective stress, sigma x, sigma y dash, sigma z dash, we are used the dash. I don't know, do you use dash or you use bar for dash? Dash, right? Same. Because the American use bar, And I know there was a running joke in the early days. I don't know whether you know Bill Lamb, the guy who wrote Soil Mechanics in MIT, Lamb and Whitman, Bill Lamb. Now, he had this running thing with a guy called Peter Rowe from Manchester, the Rowe consolidation cell. I don't know whether you're, right? And Peter Rowe used to go to a seminar and say, the problem with the American, the way they write effective stress, all the bar, is because there's too many lamb around. And Peter Rowe liked to make joke about people. He come to Cambridge and make a joke about Cambridge. And we all love it. So I'll tell you the joke when we come to Cam Clay. It's interesting, but so I'm going to use dash for this. So sigma x dash, sigma y dash, sigma z dash. The higher the effective stress, okay, the higher are the contact forces. The effective stress is not the contact forces, but they quantify the contact forces. They are not exactly the contact forces, but they quantify the contact forces. So the higher the effective stress, the higher the contact forces between particles. You just imagine if the particles are pressed very close together, okay, the higher is the frictional resistance between the particle. And the one thing that we all must understand deep down in our mind is that soil, does not usually, sometimes it does in some unusual circumstances, but it usually does not fail by particle crashing into each other. The usual way is to fail by particles slipping past each other. That's why we call it shear strength. Shear strength is because particles starts to roll and slide over each other, thereby generating a shear plane or slip plane or something like that. And so you need to have a certain amount of friction to prevent this. And so the higher the effective stress, the higher the friction. And very often, a high effective stress in many circumstances is a good thing. It's a good news. It's good news. All right? You just think in liquefaction, those of you who do earthquake, liquefaction means what? Zero effective stress. That's bad news, no? That's real bad news. Okay? So high effective stress is not bad news. So high stress in soil is not always bad news. That is the second cultural difference between soil and structure. In structure, high stress is bad news, but soil, high effective stress is actually usually good news. Okay? Okay. Now, the full effective stress equations, you can write it, the 6 equations. Actually, you can write an effective stress equation for each of the 6 stress components. And for the normal stress components, it is very straightforward. Effective stress is just equals to total stress minus the pore water pressure. So U is the pore water pressure. Sigma x effective equals to sigma x total minus pore water pressure. Similarly for sigma y effective equals to sigma y minus the pore water pressure. Similarly for sigma z. Now, when it comes to shear stress, and this is something I'm afraid to say a lot of textbooks, including myself when I teach undergraduate, I don't teach them, and so students come out totally blank this part. But in fact, when you deal with shear stress, there's no effective stress because the water cannot carry shear. The water has zero shear stiffness, it cannot carry shear. So therefore, the effective shear stress is always equal to the total shear stress. Right? So there's no such thing as effect. In fact, we don't even mention effective shear stress. We just take it as one and the same. They are just one and the same thing. All right. So you can immediately write out the full set of effective stress equation in a continuum is actually this. And in the undergraduate, we simplify it to sigma dash equals to sigma minus u. And we will keep silent on the tau, because why? When you talk about tau, the student get all confused, and then it's better not to mention it. So that's how some of the confusion may arise. But this is the full thing. And if you look at it in incremental terms, now in soil mechanics, we usually, very often when you run a finite element program, things are working in an incremental fashion. I'll explain to you what is incremental, what the term incremental means in a short while. So in incremental terms, basically the change in the effective stress equals to change in the total stress minus the change in the pore water pressure. And same thing for the change in the effective stress in the y direction equals to the change in the total stress in the y direction minus the pore water pressure. Similarly for the z direction. And for the shear stress, it's exactly the same. Okay, no difference. Okay. Now, I want to say, stop here, maybe. Stop here and say a little bit about this notion about incremental. And you'll note that actually as we move into elastoplasticity and strain hardening elastoplasticity, we'll be going more and more into this incremental thing. And the reason why you go into incremental thing is because, people always tell you, soil is inherently non-linear. Right? That's why you use more Coulomb. Soil is inherently elastoplastic. Now, the problem with this is one of the biggest cultural difference between soil and structure. Soil and structure. When you do a structural analysis, I don't know how many of you have done structural frame analysis using GT Strudel or SEP, whatever it is. When you do a static analysis, the way the structural engineer design using static analysis, like GT Strudel or the other one is StatPro. Yeah. The way they do is that they don't consider sequence. They consider load cases. Which are the primary load cases? Then I run each load cases, I run one run. There's no such thing as increment. I just put the load on straight on and run. And I got the solution. And then what I do is I combine this solution together in different ways to give me the worst possible scenario. This is what we call structural load combination. Structural load. Now, in geotechnical finite element analysis, it's actually a simulation process because the soil is non-linear. So you don't actually think of, I combine this load with that load. Because the moment the soil is non-linear, you cannot superimpose. You cannot superimpose anymore. And so therefore, what you have to do, whenever you run a finite element, this is something you must have in your mindset. When you run Plexis or when you run any finite element software, you are actually doing a simulation. So you must have that set of events very, very, very clear in your mind first when you put in your input into the computer. And there are 3 to 4, I think there are 4 sets of inputs you need. The first is the geometry, which is the mesh. The second is the material model and a parameter, which is something you need to put in some material. The third is the boundary condition. The fourth is the loading or construction sequence. And that is new. In structural engineering, you don't actually deal with loading sequence or construction sequence. In geotechnical engineering, when you do a FEM analysis, you always think through what is the sequence of load I'm going to put on. How long is it going to take? If you are doing a consolidation analysis, and if I'm going to remove this soil from this tunnel or remove that soil from a deep excavation, what is the sequence? Remove first or strut first? You know, this is always very clear. You have to be very, very clear. So what you're doing is actually going through a simulation process. You're not doing a load case combination. That is the basic cultural difference between structural analysis and soil analysis in terms of numerical analysis. Structural analysis, you don't need to do simulation. You're just doing load combination, because if you tell any engineer, hey, the structural beam has yielded, I think still can be used. I think the guy is going to flip out on you. Because most structures are designed to behave in an elastic range and preferably in a fairly linear range. If you tell people this retaining wall has yielded, I think the guy will say, I think you better stop work because you cannot carry on. But some soil will yield. Soft clay will yield very readily. The moment you touch it, it will yield. So you cannot don't yield. You have to accept yielding as part of the soil behavior. But structure, because structure is a man-made material, it's concrete or steel. So you can actually specify that it's not going to yield. In fact, structures are designed not to yield. All right? Okay, they are not designed to yield. So basically, as far as the structure is concerned, everything is linear elastic. So you superimpose them very readily. In soil, when you do soil, it's always simulation. The word is simulation. The finite element simulation. Okay? So this is very important. The mindset of doing the analysis is very important. Okay? Drain and undrained conditions, the two extremes. Now, in a saturated soil, you know that all the voids are filled with water. And in general, the water may flow relative to the soil skeleton, and the interaction between the two actually can be quite complex. If you think of it in a general sense, it can be quite complex. But so to make life easy for us, the geotechnical engineer has defined two extremes. And the two extremes are the completely drained and the completely undrained condition. I'm sure you've heard of those two words. So I want to sort of go a bit more into this to give you an idea of what is really drained, what is really undrained in a finite element analysis. So that when you use it, you get a better idea what is drained and what is undrained. You know, sometimes it's not as simple, because I talked to this guy, this very experienced structural engineer, pre-stressed concrete guru in Singapore, and he can't understand drain and undrained. So I find out after talking to him that actually this notion of drain and undrained is not so straightforward to a lot of non-geotechnical engineers. You know, so I thought maybe I better say a bit more about this. So drain and undrained. Okay, let's start with the drain condition first. The drain condition. So I have here just a general body of soil. All this little thing here are soil grains. Okay, just a general body immersed in water. There's ambient water around it, and there's this body of soil that you're considering at this point of time subjected to some external loading. All right, external loading. Now, if this soil body is relatively permeable and the water can sort of drain in and out of the soil body, okay, drain in and out the soil body, then there must be equilibrium. The pore pressure inside must be equilibrated with the pore pressure outside. Otherwise, there will be flow of water. All right, so they must be in equilibrium with the surrounding water. Okay, even when you deform the soil skeleton, the water pressure has to be in equilibrium. This is what we call a drain condition. So if the surrounding water is in a hydrostatic equilibrium, then the pore pressure in this condition must be in a hydrostatic condition, which in another way of saying, what we normally say is that excess pore pressure is 0. And if this condition is fulfilled, it is called a drain condition. It is called a drain condition. All right? That means a drain condition is one in which your pore pressure inside the soil mass that you're considering is completely in equilibrium with the surrounding or the boundary pore pressure conditions. The boundary pore pressure conditions. Okay? So there's no flow of water. Water will not flow because everything is in equilibrium. All right? And you know exactly what is the pore pressure inside the soil. You don't need to run the FEM. If you start with hydrostatic, you finish and it's drain, it's hydrostatic, then everywhere is hydrostatic. So you will know the pore water pressure. You won't need to compute it using FEM. Okay? And that is a drain condition. Okay? Now, so when we run finite element, and this is one of the things that I always remind people, when you run finite element in a drain condition, always pay attention to your pore pressure boundary condition because you must equilibrate it to the surrounding. So the question is, what exactly are you equilibrating it? You have to define the surrounding. Maybe it is seepage condition, maybe it's hydrostatic, maybe it's something else, I do not know. But whatever it is, you've got to define. All right? So this is the thing that when you must take into account. That's why when one of the questions I like to ask is when people tell me, when we interview engineers, geotechnical engineers for their PE specialist geotechnical PE. One of the questions that we usually ask is how do you define drain and undrained? What do you do when you have a drain analysis? And a lot of engineers don't know that when you run a drain analysis, you need to define the pore pressure boundary condition. All right? And sometimes maybe Plexis will define or assume it for you if you don't define. But what it means is that the guy is definitely not qualified to be a geotechnical engineer because he's not aware of what needs to be done. You know what I mean? So therefore, we usually ask this question, okay, in a drain analysis, what is your pore pressure boundary condition? So this is something I think as a geotechnical engineer, we have to, when we run FEM, we need to be conscious about. Okay? So the drain condition means one thing. The pore pressure distribution is constant, okay, or is control. Okay? In a hydrostatic condition or in a triaxial test, even when the soil is deformed, the soil skeleton is deformed, the pore pressure is completely constant and controlled. It's in a steady state. It's not changing with time. Okay? Right, and there's no excess pore water. Another way of saying is that there's no excess pore water pressure because everything is reached the final state. The pore pressure has reached the final state. Okay? So this is what we call a drain condition. Now the undrained condition is in a sense the extreme opposite. The extreme opposite is the extreme condition. And just now I talked about drain condition. All right? When you deal with drain condition, when you specify a drain analysis, you specify the pore pressure boundary condition. So you are able to say the pore water pressure inside the soil must be in equilibrium with the pore pressure boundary conditions like this. So you are telling Mother Nature, or telling the computer program, telling the soil, I want your pore pressure to be in equilibrium with these boundary conditions. Fine. Now, there is another condition, and that is that if you specify it like this, then water will flow freely in and out. If there's any, they will flow. But then you cannot control what is the volume of flow, the volume flow rate. So there are two things. I like to think of it as there are two ends to a rope. You or me as a geotechnical engineer holding one end of the rope, the soil holding the other end of the rope. In a drain condition, I control the boundary condition, the pore pressure condition. The soil control the volume flow rate, how much flowing in and out. I can't control it, he has to control. In the undrained condition, it's the opposite. I control the flow rate. In fact, I control it to no flow. No water flowing in or out. But the moment I do that, the soil controls the pore pressure. I cannot control the pore pressure. So in life, you cannot have everything and eat it. You have something, the soil has some other thing. So when you are dealing with drain or undrained, you have to be very clear which end of the rope you are holding. So in the drain condition, you are holding You're holding the pore pressure end. You're controlling the pore pressure. But do you know how much water is flowing in and out? The soil can tell you, but you cannot control it. You cannot say, I don't want water to flow and I don't want pore pressure and I want pore pressure to be constant. Cannot happen. That cannot happen. You know what I mean? That is a violation of the laws of nature. So that cannot happen. So in an undrained condition, you can say, I control this soil volume inside here. The water can neither flow in or out. That is undrained, right? But then you cannot say, at the same time, I want to control the pore water pressure. You cannot. The soil will generate its own pore water pressure. So that is the way it works. So basically, think of two ends of the rope. You're always holding one end, the soil holding the other end. Alright? It's just that you're swapping the two ends of the rope. So essentially, the undrained condition is an extreme. Okay? Not in terms of no excess pore water pressure, but in terms of no relative movement between the soil skeleton and the pore water phase and everywhere throughout the soil body. So the drained condition is one in which the pore water is allowed to come to equilibrium with the surrounding water. The undrained condition constrains the pore water to move with the soil skeleton so that there's no relative flow of water. So you are controlling, telling the water you cannot move relative to the soil. Wherever the soil moves, you got to move. But at the same time, you then cannot control the pore pressure. Okay? So hence, there's no drainage and the name, the undrained condition. Now, usually a drained condition is a final condition if you allow drainage to occur. And if you allow time for the pore pressure to equilibrate, the undrained condition is what you call a non-equilibrium condition. Usually, in a lot of construction work, it applies to short-term condition. Short-term condition. Okay? And it will occur if the deformation occurs so fast that the pore pressure has no time, pore water has no time to drain, and the pore pressure has no time to dissipate. And the best way to achieve undrained conditions usually don't allow time. Now, in practice, just saying a little bit about the way things are practiced in Singapore. Usually, if you do a FEM, okay, of course, the best way to do FEM is to say, I will run it with the soil dissipating the excess pore pressure. That's called consolidation analysis, with the soil dissipating the pore pressure as it goes along. That is the best way to do it. But a lot of engineers, somehow, I don't know why, but they are afraid to run consolidation analysis. You know? So usually the authority will say, okay, you don't want to do that, fine. You run one undrained and one drained. So one is the very short term, one is the very long term. If both are safe, I kind of assume that somewhere in between you should also be safe. You know what I mean? That is the basic assumption. So basically, the baseline is to run one drain and one undrained, or one undrained and one drain. Okay, especially in an excavation, because in an excavation, typically the undrained analysis is less conservative, but it will happen right at the moment you start digging. The drain condition will be less conservative. Is actually more conservative. Is the more unsafe condition. So you run one for the more unsafe condition and tell people, see, in the long term it will still stand up. So in the short term it stand up. In the long term it still stand up. The assumption is that in the intermediate term it must still stand up. That is the basic assumption. Okay. So if you can't do a consolidation, if you can do a consolidation, I love to do consolidation analysis. The way I do it is this. I say I can model an undrained analysis by specifying very short time. Right? I specify a drain analysis by specifying a very long time. So essentially I'm doing the same thing. One undrained and one drain. But I can explore the whole range in between. But a lot of engineers don't like to do consolidation analysis. You know, I guess they don't fully understand it, so they are a little bit afraid to sort of better don't touch it. You know. Don't touch things you don't understand. That's the kind of attitude. You know. So if we just run one drain and one undrained. So basically this is the way it works in practice. So in undrained analysis, the basic condition is that there's no volumetric change. No volumetric change. Okay. When we talk about volumetric change, the volumetric change is usually captured in terms of a parameter called volumetric strain. Epsilon V is volumetric strain. Volumetric strain. It is the change of the volume divided by the original volume of the soil specimen. And I won't go through this out of mathematics. Actually, the algebra is quite straightforward. It's just a definition of the volumetric strain. And without going through the mathematics in detail, all I want to say is the conclusion, which is the last line on the slide, which is that the volumetric strain is just simply equals to the sum of the three normal strain, epsilon x, epsilon y plus epsilon. See, that's what it is. That's in the first order approximation, as a first order approximation. And this is the typical approximation that we use. Okay? Okay, now, there is something that we need to take into account, and that is that related to this issue, how many of you have experienced running FEM especially for practical work? How many of you? Okay, you know there's always this question being asked. Should I use the undrained modulus with nu u equals to 0.499, or as Plexis would have loved it, should I use effective stress analysis, E dash, nu dash, and so on and so forth? You know what I mean? Huh? So you get this kind of, but I'm doing undrained analysis, why can't I use EU and nu u equals to 0.49? So basically, EU and nu u equals to 0.49 is actually a total stress analysis. It is actually total stress analysis. So in this section, I hope to bring you through a bit of the theory of these two approaches and leading you kind of with a clearer, possibly with a clearer idea of what is the implication of running each way. It's not that you can't run it, you can run it. It's just that you got to accept the implication. That's all. That's all it matters. You know. So basically, there's this perennial thing because some of the older programs like XCAF, they use total stress analysis. I think there are other programs that also use total stress analysis. Then on the other hand, you can run something like using effective Young's modulus, effective Poisson ratio, which is not necessarily 0.49, maybe 0.2, 0.3, 0.35, that kind of thing. And yet, you can still get answers that are reasonable. And so, the question is, what is the difference between these two approaches? Okay? So, I hope to be able to sort of cast a bit of light on that. Okay? Now, I want to first define what is an effective stress analysis. An effective stress analysis is one in which you calculate the effective stress, the pore water pressure, and the total stress. The total stress is always calculated. Alright? Now, in order to calculate the pore water pressure, you need to calculate the effective stress. Because you need to know two. The effective stress equation says effective stress equals to total stress minus pore water pressure. If you know that's the total stress, you cannot calculate the effective stress and the pore water pressure. It can be anything. But if you know one more, either the effective stress or the pore pressure, you can calculate the last one. That is the way it works. So the effective stress analysis is one in which you explicitly compute the effective stress, compute the pore water pressure, therefore compute the pore water pressure, and of course compute the total stress explicitly. This is how it works. Now, in order to do an effective stress analysis, you have to split the soil, in a sense, into two portions. One is called the soil skeleton, which is just a collection of the grains. And it has its own characteristics. That set of characteristics is called effective stress parameters. Then you have the water that has its own characteristics. And then you kind of specify them differently. Now, usually you don't specify the water, but I'll tell you why you don't specify, because the program is smart. They do it for you. Okay? So the soil skeleton and the water are separately characterized. Okay? So in order to conduct an effective stress analysis, so you need to characterize the stiffness of the soil skeleton or the strength of the soil skeleton, and this is done using effective stiffness and strength parameter. Now this is important. I use two different things. Effective stress stiffness means Young's modulus, Poisson ratio, that kind of thing. That is stiffness, modulus, and Poisson ratio. Strength is C dash, Phi dash, that kind of thing. That's strength parameter. Now this is important because when you work with Plexis, how many of you have worked with Plexis before? When you work with Plexis, Plexis gives you a lot of combination. You can mix effective stress parameter with total stress strength parameter and vice versa. You've got to be clear about what we are doing. So hopefully that's the purpose of this whole discussion, is to try to shed some light on this thing. I'm not saying Plexis is actually very, very versatile. It's just that because it's so versatile, a program that's more versatile is a program that's making more assumption. Because they also know that you cannot possibly, they try to lighten your workload by assuming things for you. But sometimes they assume something not quite correct. So you have to as an engineer said, no, in this special condition, I cannot live with this number. I have to specify my own number. That's fine. So as long as you know when to override, when to come in, and when not to come in, that is fine. So this is exactly what this discussion is all about. So to make you to give you some understanding as to how things work, so that when you work with programs, and Plexis is by no means particular in this. There are many other programs which will assume all kinds of things for you. Okay, some will assume reasonable, some will not be assuming so reasonable. So you have to be careful. So anyway, you have to characterize the strength and the stiffness of the soil skeleton. Soil skeleton. The key word here is the soil skeleton. So not the soil itself, but the soil skeleton. So you cut out the water. You cut out the water. And so this is done using effective parameters. And in this part of the course, you're doing elastic analysis. We only consider effective stress stiffness parameter. Tomorrow onwards, we'll be doing effective stress strength parameter and the effect of that. So we'll do it one at a time so that you know how the whole thing is superimposed. And we can characterize the behavior of the soil skeleton in terms of an effective stress strain matrix, where the effective stress strain matrix can be written in this form, where K dash and G dash are in a sense the effective stress bulk modulus and the effective stress shear modulus. Is that okay? Effective stress bulk modulus and the effective stress, effective bulk and the effective shear modulus. Okay? So this is the way you characterize effective stress parameter. So when you use effective stress analysis in Poisson ratio and you enter E dash and nu dash, the E dash and nu dash will actually be used to calculate K dash and G dash using the formula that I showed just now. You see, K dash equals to E dash over 3 into 1 minus 2 nu dash. That is to get the K dash. And the G dash just simply equals to E dash over 2 into 1 plus nu dash. So that's how they calculate. That's why you need two parameters, but they are all effective stress parameters. Okay? So this is what is happening inside the software. Okay, now I want to say a little bit about the relationship between effective and undrained modulus for undrained situation. Now this slide to me is something quite relevant to a lot of us who work in practice, because very often you hit something, I don't know whether in the Plexis manual or in a lot of textbook they will show, when you measure modulus in the field or in the lab, you probably end up with an undrained modulus, what we call an undrained modulus, in a saturated soil. If you do a pressure meter test, you would end up with an undrained modulus. Okay, so you get undrained modulus. They say, how do you get the effective modulus to put into Plexis? Well, the way to do it is, this is the equation. This is the equation. All right, that they'll give you this equation. Now, question is, how does this equation comes about? This equation comes about in a very, very simple way. And this is a question I love to ask, because a lot of people don't know. They say, I just follow this like that, the equation like that. I just follow the equation. I said, do you know how this equation comes about? I don't know. I said, actually, it's just one line, you know. The one line is that you just have to know that water has no shear stiffness. So the shear modulus, the undrained shear modulus, is equal to the effective shear modulus. That's all you need to know. And the undrained shear modulus is equal to the undrained Young's modulus divided by 2 into 1 plus the undrained Poisson's ratio, which is 0.5. And then the effective modulus the effective shear modulus equals to the effective Young's modulus divided by 2 into 1 plus the effective Poisson's ratio. Just rearrange the equation, putting in undrained Poisson ratio of 0.5. The answer is there, right there. One line. That's all it takes. You know. So this comes about by just assuming, the basic understanding is that there's no such thing as effective modulus or total modulus. It's one and the same thing. That is the basic key point. So that hopefully kind of clears up that particular issue. And then the next thing is drain analysis. Now, in a drain analysis, usually drain analysis poses no problem. The only problem is specifying the pore pressure boundary condition. Because at an analytical level, it's very easy to separate the effect of the soil skeleton from the water, because you know the pore pressure. The pore pressure distribution is known. It must be in equilibrium with the boundary. So if the boundary is hydrostatic, everywhere inside got to be hydrostatic. So you know exactly what the pore pressure is. So if you know what the pore pressure is, you can easily deduce the effective stress. for the total stress. So the total stress strain matrix is just given by the equations that we have before, which is equation 40. And essentially what it means is delta U equals to 0. So delta sigma dash, change in effective stress equals to change in total stress. That's all it is. Is that all right? So in a drain analysis, from a computational viewpoint, it's easy on the computer. It's not necessarily easy on the user because the user got to think about what is the boundary condition. You know what I mean? In most cases, the boundary condition can be quite straightforward. You start with the hydrostatic, you end with the hydrostatic. But in some cases, not so straightforward because when you dig a hole, all right, inside the hole, excavation, 30 meter deep, the water table is drawn down 30 meter. Outside the excavation is still somewhere high up. So what happened between this side and that side? The water will start to seep. So if you leave this hole open, just imagine now, if I leave this hole, you leave this hole open for a very, very long time, and every day you keep pumping out. Of course, you don't pump out water, it becomes a swimming pool. And then there's no issue, the water will back to hydrostatic. But supposing the contractor is very, very diligent, every day he's pumping out water, then what will happen to the thing? Basically, as you pump water out, water will seep through, right? So you actually have the long-term condition is a steady state seepage condition, not a hydrostatic condition. You know? So basically, programs that are smart enough will let you bring the boundary further out and actually move towards a seepage condition, near to the excavation. It's just something that you need to be careful about. Okay? So this is the trick about the drain condition. But internally, it's very straightforward because the pore pressure is calculated separately of the soil skeleton. Separately. It's not calculated together. So you don't have a problem. So, any questions before we take a break for lunch? Oh, the pore pressure boundary. Maybe I'll use an example to do it. Let me just try to understand you where you are, what you're asking. You're asking me about how we typically would set pore pressure boundary conditions. Is that what you're asking? Okay, let's take a very simple situation. Supposing you have a simple situation like you just have a pile cap with some piles or footing on the ground, and then this is level condition, right? And basically you're doing an effective stress drain analysis, and so you would have a finite element mesh, and then that's your boundary. All right, and just to simplify things, let us assume that initially the water table, or rather the water table is always at the ground surface. Now, when you start loading up the pile, obviously in the short term there will be some excess pore pressure around the pile, and the excess pore pressure will start to dissipate outwards. Okay, assuming that you don't change the groundwater table, this is a very simple situation. All right, then you can say that far away enough from the pile, the water pressure will be hydrostatic. So this is how you would specify your water pressure, hydrostatic pore water pressure. Now this is a very simple situation. So this means that at all times, the water pressure on the left and the right boundary are hydrostatic at all times. So therefore, when you do a drain analysis, this all the pore pressure inside here will automatically be as hydrostatic. And because the pore pressure is a drain condition, it will be hydrostatic. And because the pore pressure is hydrostatic, the total stress, the effective stress is just simply equals to the total stress applied by this group of things, the pile, minus the total stress, which is hydrostatic. So the pressure is known situation. And that's very easy. In your FEM input, all you need to do is to specify hydrostatic, thereafter no change. Alright? No change. Now this is an easy situation to set. Okay? Now, a more difficult situation would be something like that. You have a soil, and say you have a retaining wall over here, and then you come along and you remove this lump of soil gradually. Alright? And your groundwater table at the start is here, ground surface. Alright? Now when you remove the lump of soil, you obviously, hopefully the contractor is diligent enough, he will lower the groundwater table inside to here. Alright? So then, when you are running your analysis, you must make sure, A, your boundary is far enough. Alright? If your boundary is far enough, and what I'm drawing here is definitely not far enough, but I'll just have to stop here because it's right here. So basically, what you would say is that around this, now there are different ways you can deal with the situation here. You can make different assumptions. The first assumption is to say, okay, I just apply a condition to this boundary. All right. I assume that there's no water ingress through the ground surface. Now, that can be challenged because people say, what if it rains? What if there's a flood? Water can come through, which is true. So that may not be the worst case scenario. The flood may be the worst case scenario. All right. So maybe there's a 30-day flood, a 49-day flood, 100-day flood, whatever it is. Then obviously this scenario can work. But supposing you say I'm quite a gung-ho engineer, I take all kind of risks. Never mind. I'll just set this boundary, the right boundary, to hydrostatic. And then what it effectively does is to allow water to come in through here. All right, water to come into here. Okay, and then what you do is you have to set this. You have to set this boundary. Okay, this boundary to the water table, the new water table, which is you have to set this at 0 water pressure. Okay. Now you may or may not want to set this boundary to hydrostatic because I don't think it will be hydrostatic. Okay. So to me, this is more like the center line of the excavation, so there will be no flow going out. So if there's no flow going out, you cannot set a pore pressure boundary here. It's just closed boundary. It's just what we call a closed boundary. What Plexis would call a closed boundary. So you close that boundary off. No flow will go through here because you're assuming that there is a mirror image of this excavation on the other side. There's a mirror image of this excavation on the other side. Now, if you then run a seepage analysis, which Plexis allow you to do that, you will be able to see the seepage flow net coming through. And then everywhere the pore pressure will be defined by this seepage situation. So what you're saying is that after a very long time, if you keep pumping water from here, from inside the excavation, all right, you will set up a steady state seepage situation in which water will actually be flowing from behind the excavation to the front, to the excavation itself. Now, of course, you may say, I want to set up the pore pressure so that, in fact, this is higher than 0, maybe 10 kilopascal. 10 kilopascal would mean that you got 1 meter of water on here, which is something like a flood. And so you may say, I want to simulate a flood, a long-term flood, and see what happens. So these are some kind of, but it all depends as an engineer, what you think is what we call the worst case scenario. What is the worst case scenario? So this is where the engineer has to make a judgment and say, what is my worst case scenario? But once you have very clearly figured out your worst case scenario, then you can set your boundary condition properly. Now, a third example is tunneling situation. Okay, there are cases where tunneling situation is actually quite complex because if you're doing TBM tunneling, what we call tunnel boring machine tunneling, as the machine push forward, they lay the lining behind and they do tail void grouting. They grout the void behind. And so you don't know how far back the grouting will start. Okay, and that is an indeterminate quantity. So you may want to run some cases just to bracket the thing. But assuming you dig a hole here, okay, and you spray some shotcrete over here, Now, quite often, this shotcrete will not be permeable, and because it is not permeable, let's say the groundwater table is here, you will build up a lot of pore water pressure acting on the shotcrete. Okay, and sometimes the contractor will drill hole in the shotcrete to relieve the water pressure. If the contractor does drill hole, or if he's going to drill hole, then you need to simulate this as a pore pressure boundary condition. At least in this small region here, you got to treat it as an atmospheric pressure, or whatever the pressure is the tunnel, inside of the tunnel is exposed to. Usually atmospheric pressure. So you would say, okay, I will have atmospheric pressure over here. If the holes are really, really, really very, very closely spaced, you might just say, I just simply assume that the inside of the tunnel is completely drained, which is another possibility. It depends on how the work is being done. So basically, specifying pore pressure condition is where the engineer has to think through about how the work is done. So actually using FEM is not so straightforward. It actually requires a fair amount of thought process to go through the whole thing. The pity is that a lot of people are using now. I just copy the input file from the previous job and plonk into here, and then off you go. And that's when you get a lot of accidents. I hope I answer your question. Oh, undrained condition, you don't need to worry about pore pressure condition. No, undrained condition. You see, undrained condition, the assumption in undrained condition, let's say we take this problem. Start with this. Undrained condition means that the water is not flowing from here to here or here to here or anywhere. There's no flow of water relative to the soil. So if there's no flow of water relative to the soil, most programs don't even ask you for boundary condition. This is assumed to be closed, the water cannot come out, cannot go in. It's irrelevant. The boundary condition is irrelevant. Same thing over here. If you have undrained condition, you don't need to specify pore pressure condition here, pore pressure condition here, or pore pressure condition here. You don't. You will just simply assume that it is completely closed because there's no flow of water anyway. So same thing with this particular thing. So in the undrained analysis, no boundary condition is in principle needed. Okay? I hope it helps.